So now there's two parts of line. I added the pulley here. So this 20-pound or so load will only take 10 pounds of muscle to lift. Except we've got so much friction every place else it might almost be 20 pounds. Actually, forgetting about the windlass. The windlass, I'll explain the windlass on another video. The mechanical advantage of the windlass really helps. But, so here's torque. Torque or moment is a force that causes rotation. If the brick wasn't there and the crane didn't weigh so much, the weight of the load would tip the crane like that, and it would pivot around the pivot point, which is right there. Here's what it looks like. The weight of the crane, here's the weight of the crane, and the distance is 13 inches. Remember Archimedes in the bathtub? Weight times distance is how you compute what the turning force is, the torque or the moment. Mechanical engineers like the term torque, automotive engineers, torque. Structural engineers and crane guys use the term moment of force or just moment. So that's what we'll use. So the moment of the crane is the weight times the distance. You get 255 inch-pounds. I then added a brick. See the brick way over there? The brick is 36 inches away from the pivot point. So 36 times 4.7, 169.2. Add them up, we get 424.65 inch-pounds. So that's the moment of the crane that wants to, if there was no load here, the crane might want to rotate that way. Now the load, we got 4 bricks and part of the boom and the skip. This is called the skip, the fixture that holds up the load. All of that, 23.5 pounds, and the distance is 6 inches. From the center of gravity of the load to the pivot point is 6 inches. Multiply those two, that's what you get, 141. This is much greater than that, so the crane is stable, it's not going to tip over. Now, what would happen if we change the angle of the boom to 30 degrees? So cut, and I'll re-rig everything.